All right, we're going to talk about the division properties of exponents. In particular, here our standard is I can apply the properties of exponents to rewrite radical expressions and expressions with rational exponents. We're talking all of right now about these rational exponents, and we're going to talk about some division properties here that will help us out. So we've got two different properties that we're going to talk about in this video. First of all is the quotient rule, and second of all is power of a quotient rule. So the quotient of powers property says this: to divide powers having the same base, subtract the exponent. And so this is actually where our negative exponent rule kind of came from, or you can definitely see that it applies. I've got a to the m over a to the n, and that is going to equal a to the m minus n. Now, two key things have to happen here. First of all, like it said, I have to have the same base. So these have to be the same term. In this case, they're both a. Now, if we take this same exact rule and we have a to the m over a to the n, and we just choose to rewrite this and make it a to the m times a to the negative n. So in other words, what I would do is take this a to the n, my denominator, move it to the top and make it a negative, kind of working opposite. I could eventually get this same exact rule by having a to the m plus negative n power. I kind of messed that up. Let me fix that. A to the m plus negative n, which essentially is this exact same rule. So this quotient rule comes from our rule for a negative exponent by flipping this term to the top using a negative exponent, and then go ahead and adding them using our product rule. So again, they all kind of come down to our definition here. Okay? And so here's one trick that we can think about so that we save ourselves some steps if we're ever simplifying these. And it says to avoid negative exponents, look to see which exponent is larger, the numerator or the denominator, and then subtract using your rule. And your answer will go in the location of the starting spot of the larger exponent. So for example, if we have x to the third over x to the fifth, I notice that my exponent here on the top is a 3. My exponent on the bottom here is a 5. So I know that 5 is bigger than 3. And so I'm going to go ahead and I'm going to use my rule here by moving the x to the third to the bottom, and I save myself a step when I get x squared in my denominator. Okay? If I just straight ahead use my rule, and here's what I'm talking about in terms of saving time, if I just straight ahead use my rule with exponents, it would say to do this: x to the 3 minus 5 power, which is x to the negative second, but then I end up with that negative exponent and I have to move it to the bottom. So either way that you do this problem is absolutely correct, but in order to save some time, this little trick might help you to look for the exponents, which are going to be the larger ones, and then you don't have to worry about moving at the end of the problem. So we can go ahead and use some of our old rules right along with this new rule. And this one says use the quotient of powers property to simplify, and we're going to write our answer as a fraction in simplest terms. So for this one, before I worry about that property on the bottom, I might go ahead and simplify the top, where I have 4 to the 6 plus 3 power over 4 to the 4th. And I might have then 4 to the 9th power over 4 to the 4th, and then I could go ahead and subtract. And I would have 4 to the 5th power. Power of a quotient property. To find the power of a quotient, find the power of the numerator and the power of the denominator, and divide. So if I have in parentheses two things that are being divided by each other, a and b, and all of that parentheses is to the m power, then the m is applied to each term on the inside, whether it is on the top or the bottom of the fraction. Every term inside gets that exponent. So it says use the power of a quotient property to simplify the expression. So when we have problems like this, not only are we going to have these quotient rules, but we're also going to have all the rules that we have learned along the way. So inside of each parenthesis is going to get this first squared term. So I'm going to have 4 squared and x to the 5th squared over y squared squared times my second fraction, I'm going to do the same thing. Each term on the inside is going to be getting this cubed. So on the top of my fraction here, I'm going to have that y term being cubed. I'm going to have on the bottom the 2 being cubed, and I'm going to have the x cubed being cubed. And now I can go ahead and simplify a little bit further. I would have 16, 4 squared is 16, x to the 10th over y to the 4th times y to the 3rd over 2 cubed is 8 x to the 9th. And now I'm going to go ahead and I'm going to write these as kind of one big fraction. So I've got 16 x to the 10th y to the 3rd over 8 x to the 9th y to the 4th. So now when I look at it, I'm looking at my numbers, okay, and I can kind of split it up in this manner. I'm looking at my numbers to simplify as a fraction. I'm looking at my x terms to simplify as their own fraction, and I'm looking at my y terms to simplify as their own fraction. And so when I do that, I end up with 16 divided by 8, which is 2, and I have x to the 10 minus 9 power over, I've got y to the 4 minus 3. Now the reason for y that I chose to put it in the bottom is, remember, y had a bigger exponent in the denominator currently, so I chose to subtract those knowing that they would eventually reside in the denominator. And I now have 2x over y. And so you can definitely see that where we started this problem to where we ended up, it is much simplified in its current state. Let's take a look at another one. Go ahead and try this one on your own. Hit pause, and when you're ready to have a look, go ahead and hit play. Again, I'm going to square each term that is on the inside. So I would have 5 squared. I would have x squared squared over 3 squared and x squared and y to the 4th squared times, my second parenthesis doesn't have any exponents on the outside here, so I just simply have 2y to the 7th over x to the 10th. I'm going to simplify what I can here, and I've got 25 times 2. I'm going to start to group things that are like together, and I've got x to the 4th, and I've got y to the 7th. On the bottom, I've got 3 squared, which is 9, and I've got an x squared and an x to the 10th, and I have a y to the 8th. So now I have 50 as I continue to multiply here. 50x to the 4th, y to the 7th, over 9, x to the 12th, y to the 8th. Now when I look at my numbers here, 50 divided by 9, that doesn't simplify. So I know that that is going to be part of my answer. And then I look at my exponents. I know that 12 right here for x is bigger than 4, so I would have x to the 12 minus 4 power. And also for y, 8 is bigger than 7, so that is also going to be here in the bottom, 8 minus 7. And we're kind of running out of room, so 50 stands alone on the top of this fraction, and 9x to the 8th y is what's left on the bottom. One last example here. An assembly line worker increases the speed at which he can work by approximately the same percentage for the first 7 months of employment. The speed S in parts assembled per hour in T months can be modeled by S equals 10 times 1.01 to the T power, where T equals 0 corresponds to the month a worker was hired. Find the ratio of the speed of a worker after 7 months of experience to the speed of a worker after 4 months of experience. So here we go. For 7 months, it would be represented as 10 times 1.01 to the 7th. And again, this is in speed for parts being assembled. For somebody that has worked at this factory for 4 months, it's going to look like this. And when we're looking at the ratio, we're making that as a fraction. And so the neat thing about this is, as I start to simplify here, I notice that the 10s right away, they're going to cancel. And all that's left is this 1.01, which is on the top and the bottom. So I know that I have the same base here for my exponents. And I'm going to go ahead then and simplify this. So I would have 1.01 to the 7 minus 3 power. And because this is a ratio, I am going to keep the denominator as a 1. And I end up with 1.01, how about to the 4th? And then when I subtract, I get 1.01 to the 3rd over 1. And 1.01 cubed is 1.03 rounded over 1. Now that might not seem like much, but what this is telling us is that per hour, on average, somebody who has worked there 4 months can make 1 part. Somebody that has worked there 7 months can make 1.03 parts. Again, per hour. Okay? Now again, this doesn't seem like a huge thing, but if you take that times 40 hours in a week, and you take 1.03 times 40 over 1 times 40, clearly in a given week, somebody who works 40 hours can make 40 parts. The person who has worked there, though, for 7 months can make 1.03 times 40 parts, which is 41.2. So the person at this point who has worked there for 7 months can make, on average, 1.2 more parts per week than somebody who has only worked there 4 months. So it's clear to see that more efficient is the person who has worked there longer, which obviously would make sense. But in terms of your workforce and how you schedule people, this could be a valuable piece to know. And so this is just an example of how you could use an exponent in regards to workforce and production. So we've got our quotient rules here, 2 rules, and how they apply to our other rules of exponents.